In this lesson, we are going to go beyond the chi-square and look at how to complete analysis when you're using 3 or more categorical variables that have 3 or more levels within each of those variables. The learning objectives for this lesson is to understand when you should use loglinear analysis, how to run a loglinear analysis in SPSS, to correctly interpret the loglinear analysis results, and to write those results following APA style. The most important thing to remember is that in loglinear analysis, you are looking at the relationship between 3 variables, and each one contains codes that represent different categories of these variables. They can be either dichotomous or polychotomous, and that's something you have to determine when you're setting up the SPSS analysis. We have a general process that we follow, and the first thing that we do is check the expected frequencies in our contingency table. The contingency table just contains a number of cases that fall into each combination of categories, and we should be no expected counts less than 1 and have no more than 20% of those counts less than 5. I want to demo this concept going and using one of Smart Alex's tasks. We're going to look at task number 10, and it is that he was interested in whether horoscopes were just tosh. Therefore, Andy took 2,201 people, made note of their star sign, which obviously has 12 categories, and whether they believed in horoscopes, meaning that they're a believer or unbeliever. Then he sent them a horoscope in the post of what would happen over the next month. Everyone, regardless of their star sign, received the same horoscope, which read, "August is an exciting month for you. You will make friends with a tramp in the first week of the month and cook him a cheese omelet. Curiosity is your greatest virtue, and in the second week you'll discover knowledge of a subject that you previously thought was boring, statistics perhaps. You might purchase a book around that time that guides you towards this knowledge. Your new wisdom leads to a changing career around the 3rd week, when you ditch your current job and become an accountant. By the final week, you find yourself free from the constraints of having friends. Your boyfriend or girlfriend has left you for a Russian ballet dancer with a glass eye, and you now spend weekends doing loglinear analysis by hand with a pigeon for company. And at the end of August, he interviewed all of the people and classified the horoscope as having come true or not, based on how closely their lives have matched the fictitious horoscope. We're using this data set titled horoscope.sav, and you can conduct the loglinear analysis to see whether there is a relationship between the person's star sign, whether they believe in horoscopes, and whether the horoscopes have come true. So the first thing we need to do is think about the contingency table. And the cross-tabulation table that is produced by SPSS contains the number of cases that fall into each combination of categories. Although this table is quite complicated, you should be able to see that there are roughly the same number of believers and non-believers, and similar numbers of those whose horoscopes came true and who didn't. And those proportions are fairly consistent across all of the different star signs, and there are no expected counts less than 5. So let's take a look at what you need to do. We're going to open up our horoscope, and then what we're going to do is make sure, since the data is entered as frequency values, that we weigh the cases by the frequency. So I'm going to go to Data, Weight Cases, and then I'm going to select on Frequency. I'm going to select Weight Cases by, and then I'm going to move the frequency variable into the frequency variable column. And then I'm going to hit OK. Now I'm going to do a cross-tabulation table. And you do this by going to Analyze, Descriptive Statistics, Crosstabs, And we will have just 3 variables in our crosstab, whether someone believes in the star signs or not, which is believe, and then the star sign of the person, which is star believe, or star sign, sorry, and whether the horoscope came true or not true, which is this variable right here. So we're going to select believe, and we're going to drag it into the box labeled row. Next we're going to select true, we're going to drag it into the box named column, and then we have to define our third variable as a layer. And so we select star sign, and we're dragging it into the box that says layer 1 of 1. And then we have to click on cells. And I want to get my counts. So the first thing we do is you see this case processing summary, which basically just gives us a average of the total for how many people participated in the study and if we had any missing respondents. This is the cross tabulation for do they believe, did the horoscope come true, and the star sign. So did the horoscope come true? It was either the horoscope did come true or that it came true. Either that they were an unbeliever or that they were a believer. And then the total for each of the star signs. So this is 12 star signs long, 1 sign per month here, as you can see. So now that we know that we have all the variables that we met and that there are no expected counts less than 5, our assumptions are met, and we can do a loglinear analysis since we have more than one predictor. And with a loglinear analysis, the way that we're going to run it is by coming into SPSS, going to Analyze, Log Linear, and then we have to do Model Selection. The dialog box opens, and we have to select all of our variables that we want to include in the analysis by clicking on them and bringing them over as a factor. And then when the variable in the box, what you can do is you have to click on one of these, like star sign. We have to define the range. We know for star sign, the minimum is 1. The maximum is 12. For believer, we're going to define believer and define that with a minimum of 0, a maximum of 1. And the same is for true. We define that. We have minimum of 0, maximum of 1. And then you'll see how we've now defined each one of these variables. We also have to tell the fact that we need to use backward elimination, and we don't need to change. I like parameter estimates and association tables occasionally just to check those out, but it's optional. You can do all your interpretation without really needing them for this scenario that we're working through. And you click OK. And what I'm going to do is just go into the PowerPoint and walk you through the different tables and what we need to know for the analysis. So the very first thing you need to know is the data information table. We need to know just the fact that we had 2,201 cases, And then what you'll see is that this table also displays the number of levels that each factor has in the model. And since we have 3 factors, you see star signs at 12 cases, 12 levels. Did their horoscope come true with 2? And do they believe with 2? On this table, it is our initial output, and SPSS is fitting the saturated model, which is all terms are in the model, including the highest order interaction, and in this case, it's the star sign times the believer times the true interaction. And our SPSS then gives us the observed and expected counts for each of the combinations of categories in our model. These values should be the same as your original contingency table, except that you'll notice that each cell has a 0.5 added to it. So right here the count is now 56.5, 50.5, 46.5, and that's because the values all have a 0.5 added to the score. And the final bit of this initial output gives us 2 goodness of fit tests right here. We have the Pearson's chi-square and then the likelihood ratio. And in this context, these tests are testing the hypothesis that the expected frequencies predicted by the model are significantly different from the observed frequencies in our data. And our model fits the data perfectly. So both of our statistics are going to have a chi-square of 0. And then SPSS does not compute the probability when you have a perfect fit and you're in the initial output. Now we have to look at which components of the model can be removed. And the first bit of the output is labeled a K-way and higher order effects row. And underneath there's a table showing the likelihood ratio and then the chi-square statistics, where K is 1, K equals 2, and K equals 3. And as we go down the rows of the table. Now the first row, K equals 1, tells us whether removing the one-way effects, i.e. the main effects of the star sign, believer and true, and any higher order effects will significantly affect the fit of the model. And there are a lot of higher order effects here. There are the 2-way interactions and the 3-way interaction. And so this is basically testing whether if we remove everything from the model, there will be a significant effect in the fit of the model. And this is highly significant because our p-value is given as a 0, which is less than the 0.05. The next row is the K equals 2 and tells us whether removing the 2-way interactions, which is our star sign times believer, our star sign times true, and our believer times true interactions, and then any higher order effects would affect the model. And in this case, there is a higher order effect, the 3-way interaction. So this is testing whether removing a 2-way interaction and the 3-way interaction would affect the fit of the model. And this is also significant with a p-value of 0.030 because that is less than 0.05. You're indicating that we're removing the 2-way interactions and the 3-way interaction, then this would have a significant detrimental effect on our model. Our final row is testing whether we're removing the 3-way effect and higher order effects will significantly affect the fit of the model. So our 3-way interaction is of course our highest order effect that we have. So this is so simply testing whether removal of the 3-way interaction, which is our star sign times believer times the true, will significantly affect the fit of the model. And if you look at our 2 columns labeled sig, then you can see both the chi-square and the Pearson chi-square and our likelihood ratio test agree that removing this interaction will not significantly affect our model because our p-value is 0.636, which is greater than 0.05. Now the next part of our table expresses the same thing but without including the higher order effect, so we call it the K-way effects. And it lists tests for when K equals 1, 2, and 3, In the first row, k equals 1, therefore test whether removing the main effects, which is the one-way effects, has a significant detrimental effect on our model, and our p-value is less than 0.05, indicating that if we remove the main effects of the star sign, believer and true from our model, it would significantly affect the fit of the model. And in other words, one or more of these effects is a significant predictor of the data. And so the second row, k equals 2, tests whether removing the two-way interactions had a significant detrimental effect on the model. The p-value is less than 0.05, indicating that if we remove the star sign times the believer, the star sign times true, and the believer times true interactions, then this would significantly reduce how well the model fits the data. So in other words, one or more of these two-way interactions is actually a significant predictor of our data. And so the p-values are greater than 0.05 for k equals 3. And if we remove the star sign times believer times the true interaction, then this would not significantly reduce how well the model fits. Our three-way interaction is not a significant predictor of the data, but we do need to make sure this row is identical to the final row of the upper part of the table. So you'll notice this k equals 3 line right here is identical to this row right here. That's because it is the highest order effect. And so in the previous table, there were no high order effects to include in this test, so you won't see them in the second set of data. And what this is actually telling us is that that three-way interaction is not significant. Removing it from the model does not have a significant effect on how well the model fits the data. And we also know that removing all two-way interactions does have a significant effect on the model. And it does remove the main effects. But you have to remember that loglinear analysis should be done hierarchically, and so these two-way interactions are more important than the main effects. So with our partial associations table, we simply break down the table that we've just looked at but into its component parts. So we know from the previous output that removing all of the two-way interactions significantly affects the model. And we don't know which of those two-way interactions is actually having the effect. Well, this table tells us. We get a chi-square test for each of the two-way interactions and the main effects, and the column label sig tells us which of these effects is significant. A value less than 0.05 are significant. We can tell this from the star sign times believe, and the believe times true interactions being significant, but that the star sign times true interaction is not significant because your p-value is 0.465. And likewise, we saw in the previous output that removing one of the effects also significantly affects the fit of the model, and these findings confirm here because the main effect of the star sign is highly significant, although it just means that we've collected different amounts of data for each of the star signs when you look at the output and see how many are in all the categories. Likewise, in this table, we know that removing the one-way effects also significantly affects the fit of the model, and these findings are confirmed here because the main effect of the star sign is significant. This means that we collected different amounts of data for each of the star signs. The final output deals with the backward elimination, and SPSS begins with the highest order effect. So in this case, it's the star sign times the believe times the true interaction. Removes it from the model, see what effects this has, and if the effect is not significant, it moves on to this next highest effect. And in this case, it's going to be our two-way interactions. So at step 0, removing the three-way interaction does not have a significant effect. Because if you look here, our significance value is 0.637. From the value of the sig, we now know when you come down here to step 1, it's clear that the star sign times believe has a p-value of 0.037, and that believe times true has a p-value of 0.000. So those interactions are significant, but that our star sign times true interaction is not significant because our p-value is 0.465. Now we're going to look at step 2. And we see that the non-significant star sign times true interaction is deleted. So we're leaving just the remaining two-way interactions in the model. And these two interactions are then reevaluated at both the star sign times believe and our believe times true interactions are still significant and we retain them. Therefore, our final model is one that retains all the main effects and these two interactions, as neither of these interactions can be removed without affecting our model. And these interactions involve all three of the main effects because the variable, star sign, true, and believe are all involved in at least one of these remaining interactions. And that our main effects are not examined because their effect is confounded with the interactions that we've retained. So SPSS actually evaluates the final model with a likelihood ratio statistic, and we look for a non-significant test statistic. And that just indicates that the expected values generated by the model are not significantly different from the observed data. Put another way, the model is actually a good fit for that. And in this case, the result is very non-significant, indicating that the model is a good fit of the data. Our final model is one that retains all of the main effects and these two interactions. So as neither of these interactions can be removed without affecting the model, and the interactions involve all three of the main effects, our main effects are not examined because their effect is confounded with the interaction that we've retained. And SPSS will evaluate this final model with a likelihood ratio statistic. And you want a non-significant test statistic. It just indicates that the expected values are generated by the model not significantly different from the observed data. And in this case, the result is very non-significant with a p-value of 0.609, indicating that our model is a good fit of the data. So now we have to actually interpret all this. This is all the input that you need to interpret the interactions. So the first thing you got to remember is that we can collapse the data. And remember that there are following the rules for collapsing data. The higher order interaction should be non-significant, and at least one of the lower order interaction terms involving the variable to be deleted should be non-significant. So when we interpret the interactions for believe and true, we want to collapse the data across the star sign value. And to do this, the three-way interaction must be non-significant, and it was. And at least one of our lower order interactions involving star sign must also be. And that's the star sign times true interaction. So we look at this interaction by doing a chi-square on believe and true, and we just ignore the sign as if it, not really caring if it's positive or negative. Or ignoring the star sign, sorry. We want to ignore the star sign. Now, we talked a little bit about odds ratios when you calculate your chi-square test. We also use them to look at the effect size for loglinear analysis. And the odds of the horoscope coming true, given that the person was a believer, would be 489 divided by, the odds of the horoscope coming true given the person is a believer would be 598 divided by 532, which gives you an odd ratio of 1.12. The odds of the horoscope coming true given the person is an unbeliever would be 489 divided by 582. That gives you 0.84. So our odds ratio is the division of those two numbers. So 1.12 divided by 0.84. We get an odds ratio of 1.38. So the odds of the horoscope coming true were 1.34 times higher in believers than in non-believers. Now we can also look at the star sign times belief interaction just by doing a simple chi-square on the star sign and believe, and we ignore the true. So our chi-square is borderline significant. It's 0.049. So we really doesn't make any sense to compute our odds ratio because there are so many star signs. We have 12. And in most of the signs, when you look at the contingency table, there's like a 50-50 split of our believers and our non-believers. But it's only in the Aries that you notice that we're about a 30-60 split or a 40-60 split. And it's probably this difference that's going to be the most contributing to the effect that we see on star sign. So when we write our analysis, we have to look at the star sign times believer interaction. We make sure that we report the chi-squares for any of our changes, that we report any of our relevant chi-square statistics or our odd ratios for those higher order interactions. But most importantly, we always start by reporting the likelihood ratio statistic for our final model, and we denote that with the Greek symbol for chi-square. And the text would look something like this. The three-way log-linear analysis produced a final model that retained the star sign times believe and the believe times true interactions. And our likelihood ratio of this model was chi-square, degrees of freedom, 22, equals 19.58, comma, p-value equals 0.61. So you'll notice our chi-square includes the degrees of freedom with parentheses. We write the chi-square test at 2 decimal places, and we write the exact p-value. That will cover for everything with the final model. Now we have to write about our interactions. So the star sign times believe interaction was significant with our chi-square of 19.74 and a p equals 0.049. This interaction indicates that the ratio of believers and non-believers was different across the 12 star signs. And in particular, the ratio in Aries was different from the other groups, which consistently had roughly a 50-50 split. The believe times true interaction was also significant, with a chi-square of 11.61 and a p-value of 0.001. And our odds ratio indicated that the odds of the horoscope coming true were 1.34 times higher or more likely in believers than in the non-believers. If you have any questions or comments on how you can apply log linear analysis to your research, please contact me at kelsey.hall@usu.edu or through Canvas inbox. Thank you.